Hi, I'm Alistair. I'm a games designer, and in this video I'd like to teach you how you can make an escape room puzzle that uses lasers. Now, I'm recording this in March 2020 and it is a strange time in the world right now. So wherever you are watching this, if you are currently feeling unwell or if you are in isolation or perhaps your country is on lockdown, know that I'm recording this video and sending you much love from me in the UK. I'm just going to carry on doing what I do normally, and if this video is able to inform you or educate you or entertain you in just a little way while this temporary situation resolves itself, then hopefully it will have been worthwhile. So I'm sending you much love, and like I say, I'm just going to carry on doing my thing as normal, but I just wanted to get that message there at the beginning. So let's crack on. So I've had people asking me to make a laser puzzle tutorial for quite a long time, and I've been putting it off. And the first thing I want to explain is the reasons why I haven't been keen to make one. So lasers are inherently dangerous. There is no escaping that fact. You can see that this one has got a big danger label printed on it. And the restrictions on their use differs from country to country. Here in the UK we have some laser guidelines that say if a laser is below 5 milliwatts it's safe for use in consumer products, but you know, different countries have different rules and whether you have to wear eyewear and things like that, and I guess I didn't want to get into the whole arena of potentially dangerous prop design. So that was one reason. The second reason is that in terms of the actual mechanics of making an enjoyable game that works, if you've ever played an escape room that has a laser puzzle that involves you reflecting a laser beam off mirrors, let's say, what you'll notice is that actually the alignment of getting those mirrors just right to hit a small target is surprisingly tricky. If you have fixed mounts that are screwed into walls even, just slight changes in humidity and temperature can cause those optical reflectors to distort slightly, and that could mean that the puzzle doesn't work very well. So there's kind of a few issues actually in the physical use of them as well. And lastly, lasers in real life are often not quite as cool as people think they are from films like Star Wars and other science fiction things. You know, a laser beam doesn't normally just exist in space. You can't see it. You can see the dot where the laser gets reflected off a surface. But for example, between me and the camera here, I've got a whole series of laser beams currently firing, and you can't see them. I can make them appear by shaking some kind of aerosol, and if I spray it in front of the beam there, hopefully you can see those laser beams. They've been there the whole time I've recorded this video, but you haven't been able to see them unless you have some kind of fog or mist in the air. And that generates another problem because lots of people, particularly those with asthma or other conditions, actually have allergies to fog and mist. So in order to make the laser beam effect that we all associate with kind of science fiction films that makes them so cool to use, you have another health worry from things that you introduce into the atmosphere. So how do I get round all these problems to make a safe, fun puzzle that is reliable that can be used in an escape room? This is what I came up with. As you can see, it is a cuboid box, and in the bottom of the box in the middle there is a 12-volt maglock. Now at the moment that maglock is not energized, so I can take a metal object like this key, and if I place it on the magnet there it will just roll around and I can pick it up again and put it down. That is not difficult to do. So to make this into slightly more of a challenge for the players, what I'm now going to do is place this frame over the top. And this frame contains lasers here, here, here and here, and those are pointing at laser receivers on the opposite side here. So I've got 4 lasers, 2 going across, 2 going down like that, to form a kind of a grid that passes through this frame. I'm just going to place that on top of the box below it. So what players have to do is essentially reach down through that laser grid to get to the key, but without breaking any of these beams. So we've got a kind of a 3x3 tic-tac-toe grid. That, if it's broken, will activate the Arduino here, which will energize the magnet, and will lock the key, preventing it from being removed. If that happens, what players will have to do is to press these buttons on the side to reset the magnet to release it again so the key can come out. So firstly, let me just reset the Arduino so that it begins the program, and I'll show you how that works. So at the moment, in the default state of the box, the mag lock is unenergized. But if I reach in, you'll hear that beep go off, and the key, although I can wiggle it a little bit, has actually become stuck to the lock. I now need to press both buttons will release the key again. But if I reach in and break any of the laser beams, it becomes locked every time. So the puzzle that players need to do is to reset the puzzle and then reach in, not breaking any of those beams in that grid, because if they do so, they won't be able to retrieve the key. Now at the moment, we still can't see those laser beams. But so this is where I'm going to get a fog machine like this one. And because this puzzle is contained in a box, you don't need to fill a whole room with mist or fog. You can actually very easily fill this box with you see I've actually got far too much fog in there now, but you can now see the laser beams become active, and you could easily set up a pipe from a fog machine into the base of this box or something like that, so that this was triggered when the puzzle became active. Now I'm just going to actually try and now solve the puzzle. So I've reset the puzzle, the maglock is currently not active. I'm now going to try and reach my arm in very carefully without touching any of those beams so that I don't break that laser grid at all. I haven't heard the buzzer yet, and if I now retrieve the key, there we go, that is the key. I can put that down on the side, and that is how the puzzle works. So let me now tell you a bit more about the individual components I was using in that puzzle there. And obviously the main one of those is the laser module itself. So this is a laser diode, and rather like an LED is a light emitting diode, this is a laser emitting diode, and it works in a fairly similar way. So it has two wires going into it, a red and a blue. And these are the positive and the negative one. So like all diodes, polarity is important here. You have to get these wires the right way around. And this is a 5-volt laser module. So you have positive 5 volts going into this line here and ground on this one here. Now, like if you're familiar with using LEDs, you'll know that you normally have to put a resistor in series in the circuit to limit the current going to the LED. With this particular laser diode though, however, it actually has that resistor built into it. If I hold this up close to the camera and try and get my autofocus to work, you'll see a very small surface mounted resistor there that says 910. So this laser module actually has a 91 ohm resistor pre-soldered onto it, and what that means is that you can attach these two leads directly to a 5-volt power source, and the laser will simply come on and work perfectly well as normal. You don't need any additional components. It is possible to focus these as well. This ring at the top here, you can't really see, but I can rotate that slightly, and that moves the lens forwards and backwards, which allows you to focus this into a nice sharp dot. That's how you're going to get the finest laser point on these modules. So they're actually pretty straightforward to use. You can buy them in packs of 10 or 30 or 50 from your favourite online distributors, and I'll include a link in the description below. The other main part of this puzzle is in the sensors that detect whether a laser beam is falling on them or not. And for that I'm using a simple light dependent resistor like this one. So if I show you that up close. So I've used these in previous escape room puzzle projects on this channel, where you have had to shine a flashlight, for example, to release a maglock or something like that. And I'm using it in this puzzle in exactly the same way, because a laser beam, after all, is just a concentrated light beam. So the way that a light dependent resistor works is that it is a variable resistor, and its resistance falls according to the amount of light that falls on it. So if a strong light source, such as a laser beam, hits the surface of the LDR here, its resistance will go down. Now we can use an Arduino to measure, therefore, whether the laser beam is pointing at the LDR or whether that beam has been broken. But we can't measure resistance directly with an Arduino. What we're going to do instead is create what's called a potential divider or a voltage divider circuit. So the way they work, very briefly, so we've got two legs of the light dependent resistor here. We're going to have a 5 volt input coming into one leg, and then we're going to take an output from the other leg here and go into a fixed resistor of a known value. So let's say that it's 10 kiloohms. And then from the other side of that resistor, we're going to go to ground. So we've got our two resistors in series. This one varies according to whether a laser beam is falling on it or not, and the other one is fixed. And what we can do is we can take a reading, an analog read from one of the analog pins of an Arduino at the midpoint between those two resistors. Because according to Ohm's law, voltage drops in a circuit in proportion to the resistance encountered. So if the resistance on the LDR was exactly equal to the fixed resistor of 10 kiloohms, let's say, then the voltage dropped across them would be equal. And so we've got a 5 volt source here, we've got ground at this end, so the reading in the midpoint would be 2.5 volts because we drop exactly half each way. If the laser beam was, let's say, firing at this and the resistance went down theoretically to 0, let's say, what we'd find is that all of the voltage would be dropped across the fixed resistor. So our reading in the middle here would still be 5 volts. We've got 5 volts coming in here, none of it has been lost across this resistor, and it's all being dropped across the fixed resistor. So our reading of an analog reading in the middle would go up. And likewise, if let's say this was plunged into darkness, the laser beam was broken, the resistance of this would go up and a greater proportion of the voltage would be lost across this one. So an analog read in the middle would read a lower value. Now I'll show you the code shortly, but what I'm going to do effectively is calibrate the circuit when it's first fired up. I'm going to take a reading of several sample readings of each of the light dependent resistors here just to get an idea of the ambient light level. And then we will determine from that whether the laser beam has been broken or not based on how much that reading changes according to whatever the calibrated level was at the beginning. The final point to note is that these are obviously very small. This is only about, 5 millimeters across by 3 millimeters high perhaps. And as I mentioned earlier, trying to fire a pinpoint laser beam so it hits exactly on this surface is actually very tricky. So what I've done is to create a diffuser around the light dependent resistor. I'm simply using a ping pong ball that's been cut in half. And so long as the laser beam hits anywhere on that ping pong ball's surface, and I've got the resistor kind of inserted into the inside of that ping pong ball surface, what you'll find is that the light is kind of diffused all around the resistor by the white surface of the ping pong ball. And that is enough to be detected whether that is hitting the surface or not. So that increases my target size significantly, and I found that really effective. There's other kind of diffusers you can try as well. I know people use kind of like wax paper, some people use hot glue around the surface, things like that. Anything that will allow the laser beam to be detected and diffused slightly around the sensor will give you a wider surface area and just make this puzzle more reliable. So let me talk you through how I've got everything wired together, and this might seem a little bit of a complicated diagram, but I'll just talk it through step by step. So we'll start off over here with the laser diodes themselves. So here I've got 4 laser diodes which are connected in parallel to a 5 volt DC power source. And this circuit here is completely isolated from all the other components on this side, so there's no electrical connection at all between this and the other components. I used a multimeter to test each of my diodes, and they were drawing about 30 milliamps of current when they were on. So that's roughly comparable to an LED, a normal LED. You certainly don't need a beefy power supply to power that much, but do just make sure that whichever power supply you're using has sufficient current to be able to power the number of lasers modules that you use. And then on this side here, so each of my laser diodes has got its own receiver. Now, these in turn use an analog input pin on the Arduino. Now, if you're using an Arduino Uno, you have 6 analog input pins. If you have a Nano, you've got a total of 8 analog input pins. You can get a multiplexer, which can increase that number, but to be honest, I don't think you'll actually need more than 4 separate receivers. If you want to create a more complex grid or pathway that players need to navigate, you can simply place mirrors in the beams here between the laser diode and the receiver module. So for every time it bends around a corner or bounces off a corner, you can kind of split that beam into several subsections, and if any one of those subsections gets broken by the player, the receiver will detect that the laser beam has been broken and trigger the maglock. So I think 4 is plenty, but if you wanted to, you could extend that based on the number of analog input pins in the Arduino you're using. And each of these is wired in the same way. So I've got 5 volt on the red line here, and I've got the black line going to ground. And then if we just take a look at a single receiver, so let's look at this top one here. So we've got 5 volts going to one leg of the light dependent resistor, and then on the other leg of the light dependent resistor we've got a wire which is going to an analog input pin. Then we're going through a fixed resistor, and then we're going back down to ground. And the fixed resistors I'm using are 10 kilo ohm fixed resistors. So the reason why I'm using those, so I again used a multimeter and I read the resistance that I was getting from my light dependent resistors, both when the laser beam was shining on them and when it wasn't. And the values I got from the light dependent resistors I was using was that when the laser was shining onto the resistor, it was a resistance of about 100 ohms I was getting. And then when the laser wasn't there, well then it's just getting the ambient light from the room you're in, and mine was reading about 20 kilo ohms. Now those exact values that you get will vary depending on the environment in which you're using, depending on the amount of ambient light, other light sources in the room, how strong your lasers are and things like that. So you might want to test them yourselves, but the values I had were between around 100 ohms and 20 kilo ohms. And what we're doing here, we're creating what's called a voltage divider circuit. So this resistor here is varying between 100 and 20,000. If we set this resistor to be fixed at 10 kilo ohms, which is roughly speaking in the middle of that range, that's going to give us the widest range of values that we can read at this midpoint between them here. Because when this is very low, so when the laser beam is hitting the LDR here, the resistance here is going to be very low. The resistance here is constant, so almost all the voltage is going to be lost after we read the signal line here. And if that's the case, the reading is going to be very low. If, on the other hand, this is in darkness, so the laser beam has been broken, let's say, the resistance here is going to be much higher, and a greater proportion of the voltage is going to be lost over here compared to the fixed resistance of 10 kilo ohm. So that's going to change the reading the other way. So what we want to do is to pick a value here that means that the proportion of voltage lost relative to the varying resistance here is going to give us a nice range of values at our analog input pin that we can use to detect whether the laser beam has been broken or not. That's what we're trying to achieve here. And each of our LDRs has a mirrored circuit, so again they're connected to 5 volt and ground. Each one has its own fixed resistance and it's going to a separate analog input pin. The actual values that we're going to be read, when I get on to show the Arduino code in a minute, we're going to calibrate those in the code anyway. So it doesn't have to be matched exactly. We're going to take a reading when the Arduino code first fires up. We're going to calibrate it to the actual ambient level that is received on those sensors. Over this side here, I've got a speaker. That's just wired to, I'm using pin 6 as a digital output pin. And that's just to give another piece of feedback to the player to let them know when a beam has been broken and that the lock has been activated. You could instead, if you wanted to trigger a sound effect, or if you wanted to send a message like an MQTT message to a server, something like that, to let the player know that a beam had been broken, you could do that as well. But I'm just using a simple buzzer which is wired to 6 and ground. And then we've got our reset buttons here. So I've got 2 arcade buttons, and these are wired in series. So I've got a single digital input pin I'm using pin 4 here. This is wired to one side of the first button, and then the other side of that first button is wired into the second button, and then that is wired back through to ground again. So only when both of these buttons are pressed at the same time is a circuit formed here between pins D4 and ground, and that's what we're going to use to reset the puzzle. The reason for having 2 switches, quite simply, I could have had a single button switch here, just going between 4 and ground. The reason for having 2 on both sides of the box is that is designed to ensure that players have actually removed their hand from the box. They're using both of their arms to press these buttons which are on the outside of the box, which, if there was only one button, let's say, they could actually leave their arm very close to the key at the bottom of the box, quickly hit the button outside and grab the key. So this is kind of meant to be a cheat prevention mechanism, I suppose, by using 2 buttons for the reset. That's why I've set it up like that. And then finally on this side here, we've got a 5-volt relay module. So again, we've got this going to the 5-volt supply and to ground. So I always use red for 5-volt and black for ground in all my projects. So it doesn't actually make a difference electrically speaking. You could use any color cable you want, but just for ease of understanding how these wiring diagrams work, this is my 5-volt, this is my ground. And again, it has a signal line, so this is going into digital pin 2 on the Arduino, so I'm using that as a digital output, and depending on whether we write a high or a low signal to that line there, that's going to switch this relay between the normally open and the normally closed connections here. That in turn is going to allow this 12-volt power supply here to go to the maglock or not. So in its default state, we've got the maglock wired to normally open and the common connection here. So there is no connection between these 2 wires here normally. That means that the maglock is not receiving power, it's not energized, and anyone can just reach in and pick the key up. But if any of these sensors here detect a significant variation from their calibrated base state, that means that we know that the laser beams have been broken. The Arduino then writes a signal to this blue line here, which causes the relay to switch across from normally closed to normally open, and this supplies power, locking the maglock. So that's the sort of the chain of events that happens there. When this beam is broken, the resistance here goes up. That alters the analog read signal that we're getting on the analog pin here, which makes the buzzer sound play, and also switches the relay so that this becomes energized and the maglock is activated. And then again, to reset, when both of these are pressed simultaneously, that is read through a digital input, and that kind of resets the system to how it was before. And now let's take a look at the Arduino code. So it's not too lengthy this time. We've got 136 lines of code, and if you've seen any of my previous projects, you'll know that I tend to maintain a fairly similar structure for all my projects, and this one is the same. So right at the top of my code listing, I've got some constant declarations. So these are values which are not going to change throughout the duration of the project. So first of all, we define how many sensors we're going to have. That's obviously equal to the number of laser beam modules we have as well. and what are the analog input pins that we're going to use to detect those beams. We'll also say what is the digital pin that we've got attached to the relay and the buzzer, and also which is the pin that's going to be attached to the buttons that we're going to use to reset the puzzle. So these are all sort of related to pin declarations. We've also got a variable here. This is going to be by how much the analog reading of these pins here needs to vary in order to register that the beam has been broken. So if you set lower values here, then it's going to be more sensitive. If you set higher values, it's going to be less sensitive because that's by how much the reading needs to vary. But I would start with 50. That seems to be a pretty good value for me. But if you'll find that you're either accidentally triggering them or if you're finding it too hard to trigger them, then you might want to tweak that value based on the ambient light setup and things like that where you are. Then we've got some global variables. So global variables are ones that are going to be shared between various functions throughout the code. We've got two ones here. So the first one is the base reading for each of the sensors. Now, the Arduino has an analog to digital converter that will read values between 0 and 1023. So that's the full range of values you can get from an analog input pin. We're going to initially declare these as 512 because that's the midpoint of that range, but actually we're going to overwrite those values in a moment anyway when we first calibrate the sketch. We're also going to keep track of the state of the puzzle. So essentially, has any of the laser tripwires been triggered already? Have they been broken and the puzzle has become locked? Or is it still active and unlocked? Or are we just starting up and initializing the puzzle? And obviously, when we first start the sketch, we are in the initializing state, so that's how we'll define puzzle state to start with. Then we go on to the setup function. So this is what's called when the code first starts running or when you hit the reset button on the Arduino. We'll begin a serial connection. That's not strictly required for the puzzle to work, but we'll use that to send some debug output to the Arduino serial monitor, including the values that we are reading from each of these detect pins. So that will just help us to see what's going on. The next thing we'll do is we will actually calibrate those sensors. So let's see what happens there. This is the calibrate function down here. So what we're going to do is we're going to loop over each of the sensors. So for I0 to I is less than the number of sensors, we'll just increment over it. And we're going to take basically a number of sample readings from each sensor. I've set 5 sample readings. You can increase that if you want, but you probably shouldn't need to. That's just to get a reasonable range of samples of the light level that each LDR detects. And we'll use a little variable to keep track of the total value that we read from those 5 samples. And what we'll do, then we'll set up another loop. So we're looping over the sensors already. And then for each sensor, we will loop over a number of readings. And each time what we'll do is we will take an analog reading of that pin, we'll print it out to the serial monitor, and we'll also add it on to our running totals. So this total reading here, we're going to create an aggregate of 5 readings in this case. So we're going to take 5 readings, add them all together, and then once we've done that, we're then going to divide by the number of readings we took to just get a mean average. And that's what we're going to assign as the base reading for this sensor. So loop over every sensor, take 5 readings, add them all together, and then divide by the number of readings to get an average. That's what we're doing there. And then what we'll do is we'll print that out to the serial monitor, and we'll just give a 1/10 of a second delay before doing that to the next sensor as well. So what that's going to do is that's actually going to replace these values, the 512 values here which we initialized. That's going to replace those with the true values that we get from each sensor from the circuit sort of at rest, as it were. So that's our calibration function. At the moment, I'm only calling that once in setup, but if you wanted to, in theory, you can actually add a calibrate button that you could recall when the program was running if you wanted. So test whether a button had been pressed, and if so, recalibrate during running. That would be something if you wanted to add. We'll also initialize the other pins that we're using. So the reset pin, we're going to calibrate that as an input pull-up. So this is going to be pulled up to 5 volts, and then when we press those two buttons simultaneously, it's going to pull that down to ground. The relay pin, that's an output because we're going to write to the signal line to tell the relay to switch between normally open and normally closed and energize the maglock. And we're also going to write a low signal to start with. So you get two sorts of relays. You get something called active low and active high. And depending on what sort you have, you might even find that you have a jumper on your relay that you can move to switch between the two modes. But at the moment, mine is going to be low, which means that the maglock is going to be unlocked by default to start with. And because of that, we'll also update the puzzle state, just to say that we're starting off with the state of the puzzle being unlocked. So at this point in time, the key can be quite happily picked up and just lifted straight off the maglock. Okay, and then we go on to our main program loop. So what we do on each iteration through the loop while the game is running, first of all, we're going to set up a Boolean variable called anyBeamsBroken. So this is what we're going to use to say, as of right now, are any of these sensors detecting that they are not being hit by lasers, basically. And we'll set that as false initially because we'll assume that no beams have been broken. And then what we'll do is we'll actually test whether that assumption was correct. So again, we'll loop over every sensor. We'll take an analog reading of that sensor and what its current reading is now, and we'll print it out to the serial monitor just to help us debug. This is also just a little bit of extra debugging stuff here. So because we're in a loop, what we'll do is we'll insert a comma in between the readings of each sensor, and then when we get to the last one, we'll use a carriage return. So print ln is going to insert a new line after the last one. This is just formatting data to go to the Arduino serial monitor just to help you work out what's going on. This doesn't actually affect the operation of the game as such. This is the crucial line we're looking for here though. So having taken the current reading at this pin, we're going to compare it to what the base reading corresponding to this same pin was. And if the difference between them exceeds whatever the threshold value was, remember we set that at the top of the code here, we said that it was 50 to start with. So if the resistance, the current resistance that we've detected at the LDR has differed by enough that the reading compared to the base reading is greater than the threshold, we'll say that that beam has been broken. That's what we're doing here. And I mean, it may be that more than one beam has been broken, but actually we don't care about that. All we care about is that at least one beam has been broken. That's what we know about at this point here. So we do that on every iteration through the loop, whatever the puzzle state is. We test to see, as of right now, are any beams being broken? And then we use that in slightly different ways depending on what the current state of the puzzle is. So that's the next section here. So we'll use a switch statement. A switch is a bit like an if statement. It runs different branches of code depending on the value of a variable. So the variable we're going to look at is puzzle state. And if the value of puzzle state is currently unlocked, then we're going to execute this block of code here. So if we're in this state at the moment, and one of the beams has been broken, then that's when we want to make the buzzer play a tone. So we'll play 440 Hertz. This is an A. We'll play a second long duration A on the buzzer. Then we'll lock the maglock and we will change the puzzle state to locked. So this is the section of code that gets executed when my clumsy arm knocks it into and blocks one of those laser beams while I'm trying to reach the key. That's the situation that has happened in this section here. If we're in this section here, however, so the puzzle was unlocked before and no beams have been broken, so we'll just carry on as normal basically. We won't make any tone on the buzzer, and we will keep the relay pin low, and that will keep the maglock unlocked. Okay. Now, what about if the puzzle has already become locked though? If one of the beams has been broken previously? Well, if that's the case, we're in this section of code here. And there's only one action that the players can take to kind of move themselves out of this state. And the way to do that is that they must press the reset buttons. When they do that, because those reset buttons are wired through to ground, that means that doing a digital read of the reset pin will be low. So this line here means that the player is currently pressing all of the buttons that are wired in series between that reset pin and ground. And we've got another condition here as well though. This is also saying that none of the beams can be broken. So the exclamation mark at the beginning, that means that this statement is false. So we've got two conditions that must be true here. First of all, none of the beams must be broken. So that means that the players basically have removed their hands from the box, or at the very least are not currently breaking any of the beams. You can't reset the puzzle if any of the beams are currently being broken. And also they need to simultaneously press however many buttons are attached to this reset pin. And if they do that, well, fair enough. In that case, we'll reset the puzzle. So we'll put a little bit of output to the serial monitor. We'll put the relay pin back to the low state. That is going to unlock the maglock again. And for the next iteration through the loop, we'll update the puzzle state to say, okay, the state is now unlocked again. And that means that next time through the loop, we'll be back into this section again. So that's what's going on there. Switch statements, as a coding convention, you should normally add a default block at the bottom. So this happens if we get to this set of the code. That's because this case wasn't true and this case wasn't true either. Now this should never really happen in this case, but by coding convention you normally include this condition anyway. And all it says is if somehow our code has managed to get this far and our puzzle state is neither locked nor unlocked, well, just don't do anything. It should never happen, but like I say, it's just sort of standard practice. And finally, what we have here is we just have a very short delay, just because there's really no need to check whether a beam has been broken every thousands of times a second or something like that. It's just it's not going to be that accurate. So this conserves a little bit of power, slows down the code slightly by just inserting a 10 millisecond delay before going back round again. So that is my take on the laser maze puzzle, and I hope I've been able to explain the reasons why I took the design decisions that I did. So by creating it in a box like this, we've prevented the problems of the risk of lasers being fired into people's eyes, because the lasers are not mobile, they're fixed in position, and the aperture here is too small for anyone to actually get their head inside. This is purely going to be something which only an arm can be placed inside, for example. Secondly, because it's a contained space, it means that the volume of mist or fog that you need to create the laser beam effects is much smaller, and it can be contained, so it's not having to fill the whole room and risk interfering with people's asthma or other breathing difficulties, things like that. And then finally, because the laser beams themselves are actually only travelling this very short distance, the risk of them being knocked out of alignment, and because I'm using these diffusers on the receivers here, actually makes it a more robust puzzle than if you're trying to direct lasers across a very great distance, where even the smallest change of angle can kind of knock them out of alignment. So I've deliberately left the theming very simple as always. This is just a black box, but I'm hoping that you can imagine this being used for a variety of different themes. I mean, any object can be affixed to the maglock if it's attached to a metallic mounting plate. So I was using a key, but this could be a dragon's egg that you need to retrieve from a nest, or it could be some valuable artifact that has some kind of high-tech security laser system that you're stealing from an art gallery or a museum or something like that. Hopefully, you know, there are lots of examples of different escape room themes and narratives that would fit a puzzle like this. And I've tried to retain the excitement of lasers while making them safer all round. So there you have it. If you have any comments or questions about using this particular prop or any of the components I've used, please do write them below and I will do my best to get back to you. As always, I will put the wiring diagram and the Arduino Code download and everything else I've used and a list of where I purchased all the components from. I'll put those over on my Patreon account. And all my previous escape room projects are over there as well. So if you would like to, and if you are able to support me to create more tutorials like this in the future, that would be amazing. Do check over on Patreon. If you are not, don't worry about it. I will carry on putting up these videos on YouTube for free anyway, so you can follow along in the future. And wherever you are in the world and whatever situations you are facing right now, please stay safe, look after each other. Thank you for watching, and I'll see you next time. Okay, cheers. Bye.